Welcome back. In the first video we looked at what is factorizing polynomials and briefly tried to describe the remainder and factor theorem. So this is the two theorems in a nutshell. If we're trying to divide some polynomial p of x by mx plus n, if we subbed in negative n on m, so the value of x that would make that divisor 0, then whatever left over is the remainder. And if the remainder happens to be a 0, then that means that mx plus n must be a factor. Because if we write it all out, x plus n, and times it by whatever is here, then if this bracket were to equal 0, then the whole thing's going to equal 0. So the factor and remainder theorem look pretty similar, but if you sub in the value of x that makes that bracket 0, whatever left over is your remainder, and if it's 0, it's a factor. You can then use your answer. So if we find a factor, you can divide your original polynomial by that new factor and then try and keep factorizing from there. Or if you find a number of factors, then you could probably skip the whole long division and just write out your factors if they're all three linear factors for a cubic, for example. What we didn't talk about was the rational root theorem. Now, the rational root theorem is saying that sometimes when we're subbing in a value for x, say for example up here, negative n on m, it's going to be a fraction or a rational number. So how do we know what to try? We originally looked at the factors of the final term, the constant term, and tried all of those. But if we've got a non-monic polynomial here, so that means you've got a coefficient of the leading term is anything other than 1, then we could have to substitute in some fractions. So if we think about a fully factorized polynomial and what it might look like, say for example if we had 2x plus 3 multiplied by 3x plus 1 multiplied by x minus 4, then when we expanded that or expand all that out, that the four terms there would give you the constant term at the end. So 3 times positive 1 times negative 4 would give you as a minus 12 at the end. Got all this stuff in the middle. But the first term would be 2x times 3x times x, so that'd actually be 6x cubed. So when we substitute in the factor, or for the factor or remainder theorem, this first bracket would be substituting in negative 3 on 2. And for this middle bracket, we'd be substituting in negative 1 on 3. You can see that the bottom terms are actually the coefficients of the x terms. So when we expand all out, the denominators are going to be factors of the coefficient of the leading term. And likewise, the numerators all come from these constant terms, which are factors of that final term. And I could write this last one here as, rather than saying f of 4, we'd write that as 4 over 1. And we see that negative 3, negative 1, and positive 4 are all factors of negative 12, and 2, 3, and 1 are all factors of positive 6. So when it comes to trying to estimate what value of x we should be substituting in, or when we're just doing a bit of trial and error, we can always look at the fractions that we're substituting in, or the rational numbers, and the denominator should always be factors of a, which is our coefficient of our leading term. So there's our a and our a there. So that's the denominator. Whereas in the numerator are factors of d, which is our constant term at the end. So I know that's a lot to take in. You can substitute in fractions. I've probably scared off half of you already. But the numerator should be factors of the constant term at the end of the fully expanded polynomial. And the denominator must be factors of the leading term in the polynomial. So here's an example. F of x equals 3x cubed minus 7x squared plus 4. So when we're substituting in values to try and find a factor, the numerator that we're substituting in must be factors of positive 4, and the denominator must be factors of positive 3. As we can see from these two terms here. So we could sub in factors of 4. You'd have 1, 2, and 4, and they could all be positive or negative. Alright, and down the bottom we'd have factors of 3 or 1 and 3, and they could be positive or negative as well. So, for example, I might try 1 over 1, which is 1. Or I might try 2 over 1. Or I might try negative 2 over 1. Or I might try negative 4/3, for example. But I wouldn't try 3/5. And I wouldn't try positive 3 because it wouldn't fit this condition here. So it narrows down the amount of terms you're going to use trial and error for. So let's have a look at this and try and see if we can factorize using the rational root theorem. So again, I'm going to leave that part there. I'm going to try and sub in some value for x where my remainder would be 0. So I'm going to pick easiest one. I've got 1 in both the numerator and the denominator. And I look at the sum here. I've got 3 times something minus 7 times something plus something. So I'm going to try positive 1, which is 1 over 1. So let's substitute that in. I'd get 3 times 1 cubed minus 7 times 1 squared plus 4. So I'd get 3 minus 7 plus 4 equals 0. So therefore, x minus 1 is a factor. Alright, I could then do my long division, but let's keep going. Let's try another one. Now, if I put in a negative there, I'd get negative 3 minus 7 times negative 1 plus 4. Now, shortcut, if you want to use your CAS calculator, let's have a look. We can go to our main, clear whatever you've got in there. So clear all. And let's define. So we go to keyboard, math 3, define the function f of x. And let's make it equal to 3x cubed minus 7x squared plus 4. And then we can just substitute in values straight away for f of x and go, well, let's just check what I did was right with positive 1 equals 0. So I can go, well, let's try negative 1, see if that works. And I can work my way through all of those combinations of factors. Negative 6 doesn't help me because I want it to be 0. Right? But if I was doing a long division, I could check I got my remainder right. So what else we got? We've got positive negative 2. So let's try 2 over 1. And hey, there's 0. So f of 2 equals 0. So therefore, x minus 2 is a factor. And may as well keep going with our CAS. Let's try f of, let's keep going. Let's go 4 over 1. So we could try positive 4. 84 doesn't work. I'm just going to go back up here, put a minus in. 300 doesn't work. Let's make it negative 2. Does that work? Negative 48. So whole numbers aren't working, so let's try factors that have a rational number. So I'm going to try 1 over 3. Alright, I'll start with my smallest 1/3. Equals 10 over 3. Let's try it as a negative 1/3. Nope. So what are my other options? I can try 2/3 then. So I've got factors 2 here at the top. So let's put negative 2/3. There it is. So there's my third and final factor. F of negative 2 on 3 equals 0. So therefore, I would have, from my brackets here, if I was substituting x, remember, I'd have plus 2 there from the numerator, and the coefficient there from the denominator is a factor. So my final answer, going back to my original question, this whole thing at the top must equal x minus 1 times, now I've forgotten, x minus 2 times 3 of x plus 2. Now check that just quickly. Negative 1 times negative 2 is positive 2 times positive 2 equals 4. So that works out. And I've got positive 3x cubed at the front. So I didn't do any long division there, and I just used my rational root theorem to limit the amount of possibilities there were. Now if this was a tech-free, once you've got x minus 1, you can quickly do a division there, use a synthetic method, and then you just factorize in a quadratic using your skills from yesteryear. One last example. Now I know I went through that pretty quick, but you can hopefully pause and rewind and watch that at your own pace. We've got the values of a and b, and find the values of a and b and factorize polynomial p of x, given that p of x is divisible by x minus 1 and x plus 3. So from the question, when it says divisible, that means the remainder equals 0, or it means that x minus 1 and x plus 3 are factors of p of x. So knowing that, we can say, therefore, p of positive 1 must equal 0, and p of negative 3 must equal 0. So we can use these two bits of information to find two equations, which should be enough to find a and b, two unknowns. So let's set up p of 1. We should get 1 cubed plus 1 squared lot of a minus x, not x, minus 1 plus b. So that's one equation. All of that equals 0. So if we tidy it up, we've got 1 plus a minus 1 plus b equals 0. 1 minus 1. So therefore, a plus b equals 0. The second bit of information we have was p of negative 3 equals 0. So p of negative 3, let's substitute that in for x. I'd get negative 3 cubed plus a times negative 3 squared minus negative 3 plus b equals 0. Negative 3 cubed would be negative 27 plus negative 3 squared is positive 9, so 9a. Subtract negatives, so it's plus 3 plus b equals 0. Just be carefully positive negatives there. Now let's tidy this up. Minus the 27 to the other side. Give me 27 there. And then I'm going to minus a 3, so give me 24. And I'm left with 9a plus b equals 24. So I've got two equations. A plus b equals 0. And 9a plus b equals 24. And I can use some simultaneous equations to solve this. Now, just so I don't have negatives, I'm going to move this one up here. And that's my equation 1. And that can be equation 2. And I'm just going to do 1 take away 2 so I can get rid of my b's. So 9a minus a equals 8a. b minus b is 0. 24 minus 0. So therefore 8a equals 24. So a must be 3. Sub that into either equation. Easiest one to substitute is to equation 2. So therefore 3 plus b equals 0. So if I sub into equation 2, I get 3 plus b, so therefore b equals negative 3. There's my two answers. So find the values a and b, and then factorize that polynomial. So if I know my two factors, x minus 1 and x plus 3 are factors, and if I put that in, let's have a look. That means my original function would become x cubed. So p of x equals x cubed plus ax squared. So x cubed plus 3x squared. It was minus x and then plus b, so that's minus 3 at the end there. And that factorizes down. I've got x minus 1 is a factor and x plus 3 are factors. I could try and find them there. I could try and find my other factor using my root theorems. Let's just do another quick long division to show you how it works. So I've got, let's use the 1. So if x minus 1 is a factor, then putting plus 1 out there, I would have 1, 3, negative 1, negative 3, and 0. So 1 plus 0 gives me 1 times 1 is 4, 4, positive 3, 3 is 0. So I end up getting all of this is equal to x minus 1 times x squared plus 4. I'm getting my coefficients from down here. 4x plus 3. And factorizing that, I know I'm looking for x minus 3 as well. So x minus 1 Factorizing that quadratic, factors of positive 3 that add up to positive 4. So that'd be x plus 1 times x plus 3. And I knew in the original question x plus 3 was a factor, so I know I've got it right there. I could have tried to use my root theorem, subbed in positive and negative 1 if I wanted to, and would have found the other one. Doesn't matter how you get there, as long as you're following why you're getting there and you can explain it. So hopefully these wordy sort of rules here start conceptually making a little bit more sense. This one I might do a video of for our next lesson. Just some special case. You've got the sum or the difference of two perfect cubes or two cubes, then you can use that as a shortcut rather than have to go through the whole process. But the main thing to take out of this video is with the root theorem, when you're trying to find the factors, you're doing a big guess and check, like we were for this first example. Where did it begin? This first example here, the factors that we're trying to sub in, the whole number at the end, the constant term, give factors of that go in the numerator, and the leading term's coefficient go in the denominator. Okay, all the best.